Okay, hi guys. Today we're going to work on more imaginary numbers. Okay, so we're dealing with the process of imaginary numbers. Let's review quickly what we've talked about before. So imaginary numbers. We said why do we even have imaginary numbers is because when I take a square root of -1, this does not exist, right? This is not a real number. This is not real. Because you can't take a square root of a negative. Because what do square roots say? A square root is what number, okay, what number when I square it gives me this inside number. If I say square root of 4, we say 2 because 2 squared gives you that 4. Or you can say 2 times 2. Twins. Yeah, twins. But there's no twins for me to get -1. It's either 1 times 1 or -1 times -1. And none of these will give me -1. Okay? And the same thing for any negative square root. Because the way we get a negative is we say we multiply positive times negative, and positive and negative are not twins. Okay, so they always have to be the same number, plus plus or minus minus. But since to get a negative we need a plus and minus, to get a -1 we would need a +1 and a -1. Whoops, I don't know where I wrote that. We need a +1 and a -1. That's not going to work, and that works for any negative square root. If I wrote square root of -4, this would be a -2 times a +2, and these aren't twins. They're not a perfect square, right? A positive and negative number, they're not the same thing. So there's no real possibilities. So what we did is we said instead, by definition, square root of -1 is going to be imaginary. So if I do give you guys a problem that says square root of -4, we would first take out the -1, and then we would say this is I, and then a square root of 4, which is now possible. We can take a square root of 4, is 2. So we rewrite it as 2i. So you first have to take out the negative, and then you can proceed with your regular square roots, your regular programming. We had a couple of tricks with I, is that if I have just one I, a square root of -1 is just one I. But if I had I squared, this said, well, what's -1 squared? It doesn't exist because we can't do processes on imaginary numbers. So instead, we're going to say, hey, this is really by definition -1. Okay, so I squared is really by definition -1. Then I cubed, we said was just I squared with an extra I to it. So that made it a -1 times I, which was -I. This is just again review. I to the 4th. If we simplify as I squared and I squared, 2 i's, that's -1 and -1 become +1. So we always reset at every 4th I. So we gave us a couple examples in our game. If we said I to the 5th, this is really, hey, can I divide 4 by 5? Well, you get a remainder 1. That's a remainder 1. Only one I left. If I say I to the 21, can I divide 4 by 21? Yeah, but with a remainder 1, remainder 1i. How about I to the 23rd? If we divide if we divide 23 by 4, we have a remainder of 3, so we have I cubed left over, which reduces to, or simplifies to I, -I. Okay, and that comes out back right here. Our example, I to the 101, 101 Dalmatians here. Well, we could divide 101 by 4, remainder 1. So that's why it's just I. What happened to all the other sets of i's? Well, remember, they become 1 times 1 times 1 times 1 times 1. As many ones as you want to write. I to the 4th, I to the 4th, I to the 4th. Every time you have I to the 4th, that just becomes 1. And 1 times 1 times 1 times 1 is just 1. So we reset. An example of this was me saying my I clock, where we have I squared, I cubed, and then I to the 4th. And this becomes -1, -I, and 1, and then we reset. So we just walk around the clock, and the i's just reset. Okay, So we had some problems for IXL that we were practicing. Like for instance, what happens when I'm multiplying i's? What if I say 3i times 2i? Well, we multiply the real numbers, we multiply our regular numbers, and that's 6i squared. We simplify, well, I times I is I squared, just like in algebra, x times x is x squared. And this changes to a negative 6. Can I add imaginary numbers? Well, 2 plus 3i, we're done. And we haven't talked about this, so this is one of our new terms today. This is what we call a complex number. A complex number is a number made up of real and imaginary numbers. Okay, a complex number is this idea, it's made up of real parts and imaginary parts. Real parts and imaginary parts. And this is what we describe a complex number as. You can actually graph a complex number. We can graph this. And the graph of a complex number looks like an XY graph, except we're going to say this is real and imaginary. So instead of being X and Y, our plane is going to be real and imaginary. And it's like the dumbest graph in the world. It's like the easiest graph. The only thing is you just have to have experience looking at it. So how do I graph this number 2 plus 3i on this imaginary plane? Well, the real number was 2. So you go 1, 2. That's 2. What's the imaginary number? 3. 1, 2, 3. 1i, 2i, 3i. And we just put a dot. So this is the graph of 2 plus 3i. That's the point. Like, that's a point on the imaginary graph. So this is our complex number, and our complex number can be graphed in a real versus imaginary plane. I'm not kidding. This is really it. What if I give you guys another number? What if I give you guys negative 1 plus, let's say 1 plus I. Okay, 1 plus I. Okay, if I graph 1 plus I here, negative 1 is over here, plus I is up here. This is negative 1 plus I. Let me write that in red maybe or something. So if I'm asked to graph something on the complex, so Alex asked, is this a complex number? Well, once I complete it, once I multiply it out, it's actually a real number. Okay. So if I write 3i times 2i, you have to first simplify it, and then once I simplify it, we'll realize that is just a real number. This is negative 6. So if you can simplify it, yeah, simplify it. Now let me give you guys a problem. If I say 2 plus 3i plus 4 minus I. Okay. So you worked on this in your homework. So we're going to combine like terms, essentially just like x's. We treat these just like x's. I have 2 and 4. Those are like terms. 2 plus 4 is positive 6. 3 and negative I. That subtracts out to become a positive 2i. That's it. So this is a complex number. And it's complex because it's part real and part imaginary. Part real and part imaginary. Now, with complex numbers, we have something called conjugates. So complex conjugates. And a conjugate number, it's going to be a useful tool to us in what we're going to do today. So here is our idea of a complex conjugate. So a conjugate, I'm not sure if you guys have done this before, but let's look at it. A conjugate is, if I say 3 plus 2i, the conjugate will be 3 minus 2i. And there's a purpose to this, okay? There's a purpose to this. The conjugate of 5 minus 4i, the conjugate is 5 What do you think the pattern is? 5 plus 4i, okay? What changes is not the front value. What changes is that middle value, okay? If it's a minus, becomes plus. A plus becomes minus. And that's what our conjugate does. Our conjugate is we're going to take this weird frame of a complex number. We actually also do this for square roots. If I say 1 plus square root of 2, the conjugate to 1 plus square root of 2 is 1 minus square root of 2. The conjugate of 3 minus square root of 5 is 3 plus square root of 5. Okay. And there's a reason why we have these ideas called conjugates. Are we just trying to flip the sign? No, there's something very specific about what a conjugate does for us. Now, we're going to multiply these numbers right now. I'm going to say, let's take my first example, 3 plus 2i, and we're going to multiply by 3 minus 2i. 3 plus 2i and 3 minus 2i. And I want to show you something kind of interesting. This is like if I wrote x plus 2 and x minus 2. If you remember, this is going to be something called a difference of two squares. But if you remember us multiplying two binomials that were opposite signs, what happens to the middle term? Let's write it out here. X times x is x squared. X times 2 is negative 2x. 2 times x is plus 2x. And 2 times negative 2 is negative 4. Take a look at these middle terms here. And this is what you want to pay attention to right here. Whenever you have conjugates, the middle term always cancels out. Okay? Is this always going to be true? Let me give you another example real quick. X minus 100. Oh, x minus 10. X plus 10. Okay? Look at these. These are plus and minus. X squared plus 10x minus 10x minus 100. Take a look. The middle term always cancels out. So x squared minus 100. And this is a simple clue about why we're going to do this. Let's take a look. When I'm multiplying conjugates here, complex conjugates, we end up with 3 times 3 is 9. Easy peasy. 3 times 2i is negative 6i. All right, so we're done with the 3. Let's work on the 2i. 2 times 3 is positive 6i. And 2 times 2 is 4, so negative 4i squared. Something kind of interesting here. Look here, what happens here, what happens here? Negative 6i plus 6i, they always are going to cancel out. Okay, when you have conjugates, the key thing is it's going to cancel out your middle terms. And it's going to show us something kind of cool. It's going to cancel out our imaginary terms. So it's 9 blank. Now I want to go ahead and simplify this real quick. What is negative 4i squared? And here's something kind of cool. It will always be a negative at the end because a positive times a negative gives you that negative. So positive times negative is a negative. But what does I squared we say do? I squared, is that negative 1? So it always makes it into a positive. And we are left with positive 13 as my answer. We started off as a complex number. And when you multiply conjugates, the number isn't complex anymore. It's actually a real number. So this is an important takeaway. If I want to get rid of a complex number, I have to multiply by its conjugate number. If I want to get rid of a complex number, I need to multiply by its conjugate. And that's going to be important for us in our skill today. Okay, let's do this one more time. If I say my example was 5 minus 4i and 5 plus 4i. Now, we could take our time and multiply these together. 5 times 5 is 25, yes? 5 times 4 is 20, so positive 20i. 4 times 5 is negative 20i. And 4 times 4 is negative 16i squared. Now, what do you notice automatically cancels out? Okay, what do you notice automatically cancels out? 20i and negative 20i, right? Those automatically cancel out. What happens to I squared? This is really negative 1, right? And is a negative and a negative a positive? So this is 25 plus 16, which is going to be 30, 41. Now, hopefully you kind of get what we're doing here. Now, I'm going to show you the pattern of when you have conjugates and why conjugates are important for us to be able to do them quickly. If I say 2 minus 3i, well, did we just do this? We just did this, darn it. Oh no, we split it around. So 2 minus 3i, what would the conjugate be of 2 minus 3i?
2 plus 3i.
Thank you, 2 plus 3i, perfect. Now, we could multiply this out, and we could spend all our time and write this whole step here. But I'm into about seeing patterns. So for sure, the front's going to be 4, right? 2 times 2 is 4. The back, what's 3 times 3? 9. But that's a negative 9, right? But isn't it going to be negative 9i squared? Which is going to force it to be a positive, and we're done with 13. What about the middle term? Don't bother doing it. We've seen the pattern before. The middle term would have been a plus 6i and a minus 6i. And guess what? They were always going to cancel out. The conjugate's middle terms always cancel out. You can skip that term. You can skip that step if you remember that they cancel out. And this negative 9, see, negative 3 and positive 3 should have been negative 9. But since we know it's going to be I squared, it flips to a positive. So it's really just squaring the back and squaring the front. Squaring the front, squaring the back. Here we go, let's do another one. 7 minus 2i. What's the conjugate of 7 minus 2i? 7 plus 2i. If I multiply these out, can you guys come up with the answer in less than 10 seconds? Even without doing any work. We know for sure 7 is 49. We know for sure in the back it's going to be a negative 4i squared, which becomes positive 4, 53. We are done. Okay, so this is the cool thing about conjugates, is that when I'm multiplying conjugates by each other, it actually cancels out my imaginary. The same thing actually goes for square roots. If I was doing this as a square root problem, let me show you a simple square root problem. 1 plus square root of 2 times the conjugate 1 minus square root of 2. Since we know we have conjugates, look, that's going to be a positive square root of 2 and negative square root of 2. The middle term was going to cancel out anyways. So we just have to do the front and the back. Oops. This is just a hint for when we look at square roots. Okay, so what we're going to talk about today is our next skill is about what if I'm dividing imaginary numbers. We talked about multiplying, that seems pretty easy. Now dividing imaginary numbers. So if I say something like 3i divided by, so let's go division. 3i divided by 2i. Okay. Treat this like x, just like regular x. The i's cancel out, we're left with 3 over 2. So i's are treated like x. Okay, we can move them around, shuffle them around. If I say 6i squared divided by 2i, these could divide out, and we're left with 3i. Okay. Now, here's an issue. If you remember a rule in Algebra 1 where we say we don't like square roots on the denominator, you guys remember this rule? We don't like leaving. This is a bad, right? Don't like square roots on the bottom in the denominator. So if you remember how we got rid of this is we multiplied the bottom by a square root of 2 to the top and bottom. And rewrote this as square root of 2. 2 times 2 is 4. Square root of 4 is 2. So again, if you remember that we don't like square roots on the bottom, we don't like leaving our pants down, we are going to rewrite this with a square root, move to the top. So to get rid of a square root of 3 on the bottom, we multiply both sides by a square root of 3 on the bottom and the top. And 3 times 3 is 9, square root of 9 is 3. Freedom! Let me do this a couple more times. If I say 2 square root of 2 over square root of 3, we don't like the square root on the bottom, and I can't simplify that anymore. So I multiply square root of 3 on the bottom and on top. So that's a simple rule. Just multiply by the same exact square root. In this case, this would be 2 times 3 is square root of 6 over 3. And you can't divide the 6 and 3 because one's the size of square root. If I wrote it as one big fraction, 5 and 7. Okay. Well, let's go. That's not a square root on the bottom. It's a square root over the whole thing. But in actuality, we have to change it. We have to split it. And then we have to get rid of the square root on the bottom. 5 times 7 is 35. And square root of 7 times square root of 7 is just basically 7. Now, the same thing happens if we have imaginary numbers on the bottom. If I write 2 over I, the thing is, this I on the bottom is like, remember we said this is the same thing as a square root of -1. An imaginary number is just another way of saying square root. And we don't like square roots on the bottom. So what we're going to do is we're going to multiply by an I. That's it. But you got to be careful here, because 2 times I is 2I great. But what's I squared? They don't cancel out. They become I squared, which is, let me rewrite this. I squared is -1, okay, -1. So when you multiply by an imaginary number, careful, what does that new imaginary number, that product become? I squared is actually -1. So this is actually -2I. So from start to finish, you have to make sure you rewrite that imaginary number. Let's do this again. 5I divided by, let's give you guys I squared, okay? So I could here just cancel out, but here's actually a trick. Here's my next trick. What I value do we like? I to the 1, I to the 2, I to the 3, or I to the 4? Which I value do we like the most? I would say I to the 4th. If I look at I to the 4th, doesn't that just become 1? So here is a, thank you, Eden. I like 4s. So here the trick is, if I could get to 4s, this problem actually becomes a little bit easier for me. I just have to treat the denominator as just 1. And the top will actually deal with all my other i's problems. I cubed is -5i. Let me do this again. I'm going to make this a little harder now. If I say I to the, let's say, squared over I to the 7th. Okay? So we could try simplifying this, but instead, I to the 7th isn't a nice I, right? But what's an I could get to? What's an I would like to get to? Remember, we like sets of 4, okay? We like sets of 4. So how many i's could I give this to make this into 8? If I just give it one more, doesn't this become I to the 8th? And what's I to the 8th? I to the 8th is just, whoops, is just 1. Remember, every 4 i's gives us back to 1. This is just 5i cubed, which we know is -5i. Let me say this again. Let's give you guys another one. What if I say 6 over I to the 19th power? Man, that's a huge I value. And we don't like that. How many i's could I give this to bump it up to 20? Because 20 is an easy divide by 4 value. It's an easy set of 4. Doesn't this just need one more I? This is 6i over I to the 20th. And we know I to the 20th is just 1. So we're just at 6i. Okay, so when it comes to i's on the bottom, not that bad. Now here is the reason why we learn conjugates. And this is the main reason why you will see them. Is because what if I write this now? 1 over 2 plus I. There's an imaginary number on the denominator. And now this is the hardest skill. This is a skill that we have to work on. This is like the hardest part of this class today. Is that when I see an imaginary number as a complex number, you can't just multiply by I to try to get rid of it. It's almost like if I multiply I here, sure, but doesn't the 2 now get the I? Like, man, it's like washing dishes with dirty hands. The dirt just spreads. You're not cleaning anything. So the trick is, what can I multiply 2 plus I to make it not imaginary anymore? What can I multiply 2 plus I to make it not imaginary anymore? And if we look here, what we've been working on with is if I multiply imaginary numbers by its conjugate, the answer is no longer imaginary. So thank you, Eden. The answer is multiply by 2 minus I. We multiply by the conjugate. And that is the trick to these problems. 2 times 1 is 2 minus I over. Now, here's what we're going to do. You could write down all the steps here, but we talked about the trick about multiplying conjugates. Okay, let me go over the trick again. 2 times 2 for sure is 4. The back, I times negative, I is negative I squared. You can write that. But do we have to write the middle numbers? Negative 2i plus 2i. What was going to happen to those middle terms anyways? They were always going to cancel out. This becomes 4 plus 1, because I squared is negative 1. So negative 1 becomes a positive 1. And we're left with 5 here. Okay, let me do a couple more examples here to show you that this is actually really quick. 3 over 4 minus I, okay? What's a conjugate? I don't like imaginary numbers on the bottom, so we multiply by the conjugate. 4 plus I. 4 plus I. So we have to multiply that into the problem. On the top, 3 times 4 is 12. 3 times I is 3i. That's fine with me. And you can do this next step in one step. 4 times 4 is 16. We know negative I times I is I squared, so it's going to be plus 1. How did I do it so quickly? Again, negative I squared is a negative 1, which is a plus 1. And one thing you want to realize about conjugates, they always become positive at the end. It's always a plus. And that's going to be 17. Done. 4 over 3 plus 2i. Okay? What's the conjugate of 3 plus 2i? 3 minus 2i, right? If I write it on the bottom and the top, let's actually do the top first. That's going to be 12. 4 times 3 is 12, and 4 times 2 is 8i. And then we're going to write this. 3 times 3 is 9, plus 4. Why did I jump to plus 4? Because we know it's going to be a positive already, because I squared makes that negative 4 into a positive 4. 13. Done. Sure. I'll do one more. Let's do another. 5 over, let's say, 6 minus 2i, okay? So I don't like the imaginary numbers on the bottom. So we're going to write instead 6, what? 6 plus 2i. 6 plus 2i. Let's multiply the top. 5 becomes 30 plus 10i. The bottom, we could say 6 times 6, 6 times 2, 2 times 6, 2 times 2. We could do that. But we said that conjugates, the middle terms always cancel out. So we just have to worry about the front and the back. 6 times 6, the front would be 36. The back, I'm going to take my time, negative 4i squared, because 2 times 2 is 4, the negative sign. Yep, that's right. And then what happens to this I squared? It always makes that negative to a positive. So 36 plus 4 is 40. And in this case, we could reduce by 10. This would have been 3 plus I over 4. Just to talk about reducing, I can divide everyone by 10. That's right, Aaliyah. And then that negative, so that I squared becomes a negative, so it makes the negative 4 into a positive 4. Okay, one last step. Here is the epitome of ugliness. What if it was a binomial on top? What was it? 5 plus I over 2 plus 3i. Okay, now this is a complicated problem. This is the most complicated problem that you will see when it comes to conjugates, but it doesn't change our rule. We say 2 minus 3i and 2 minus 3i. Okay, now for the top, we will have to distribute all these values. Okay, so let's go ahead and do it. 5 times 2 is 10. 5 times negative 3 is negative 15i. Great. I times 2 is 2i. And I times I is negative 3i squared, which becomes a positive 3. Again, negative 3i squared becomes a positive 3. We have like terms. So it's going to be 10 plus 3 is 13. And negative 15 plus 2 is negative 13i. That just turned out to be 13 over 13 minus 13. On the bottom, though, is actually our easy part. Since it's a conjugate, 2 and 2 make 4, and 3 and 3 make 9, so it'll be plus 9. Why? Because negative 3 times 3 is 9, right? Negative 9i squared becomes a positive 9, and that's just 13. Well, that was a freaky number. How did this work out? Imagine if today was Friday the 13th. This would reduce down to be 1 minus I. So when the problem got more complicated, that's fine. Just deal with it with the skills that we've learned. We just multiply these like a binomial. They do simplify, but I squared, remember, flips the sign. And the bottom is actually the easiest part. Okay? So this is a question that you might see on the SATs. They'll give you a problem and say, hey, simplify it. And you're like, what the crap? How do I simplify it? And the gimmick was to remind yourself, oh, these are conjugate problems. I need to multiply by the conjugate. Okay, the last problem, all we did was, only difference part was we multiplied 5i by 2 minus 3i. That's the only difference. Which sure, it looks messy, right? If you have messy inputs, you're going to have messy output.